everyone hasn't figured out what they're speaking about. So the talk today is Patrick Flandrin, and we were just discussing that he's been coming to the Newton Institute for some time. He was here in '98 when there was a non-linear and non-stationary time series analysis program. I think you were here also in 2008 when there was the high-dimensional data.
No, I wasn't.
No, you deny it. You deny everything. So today he's going to talk about wavelets in the making. So it's going to be the notion of scale and networks.
Okay, thank you very much. So, when I chose to talk about this, I decided to speak about something which is not exactly classical topics, which would be statistical network analysis in the sense of the program, and I'm involved in other stuff which will be more detailed in the workshop we'll have in December. But I chose to talk about that because I think it's interesting from a general point of view, and also maybe it could open some discussion. So I'm interested in wavelets. So maybe not everybody knows about wavelets. So what are wavelets? Basically, wavelets are some kind of I would say, avatar of the Fourier analysis, in the sense that's something which is local as compared to classical Fourier analysis, and which is also multi-resolution. And one of the major advantages of wavelets is that it somehow naturally sparsify signals, images, structures, and so on and so forth. And so this was extremely interesting, especially in compression. And this led to a number of results, including the definition of new standard like JPEG 2000, based on wavelets rather than on DCT. And I will not enumerate all the application that has been found for wavelets in most areas of science, in the sense that now wavelets is some kind of natural keywords. So the interesting thing is that the wavelet story is not that old, because we can say that it all began in 1984 with a seminal paper by Grossman and Jean Morlet, which was more in applied mathematics. And immediately after that, it was followed by a number of other works, either in mathematics by people like Yves Meyer, in mathematics and physics, Inge Dobschi, in applied math, Stéphane Mallat, in statistics by David Donoho and other people. And so the field quickly grew and became something extremely important. And I would say that in the late 80s and in the 90s, it was really one of the hot topics in the signal processing, data analysis, and everybody was talking about wavelets. I would say a little bit like now when everybody is doing deep learning. So this was kind of the deep learning thing for the 90s. So if we think about the folklore which is attached to wavelets, there are a number of remarks. And the first one is that it's typically something which is an interdisciplinary study. And if we think about the first meetings that were held about wavelets, that was really a gathering of a small number, reasonably small number of people, but coming from very different areas. And then progressively, what is well accepted by people is that we have seen the emergence of kind of a new paradigm. And this, in some sense, was also some form of reshaping of the scientific landscape. And this is a kind of thing that happens from time to time, where some new concept is just emerging, and then people are thinking a little bit differently about what they did before and what they will do after, and the scientific landscape is not exactly the same. We see this with new journals and things like this. And so what we are interested in is maybe to go a little bit beyond this folklore idea about wavelets, and to think about, is it possible to see this for a more quantitative and objective, in some sense, point of view. And for that, we chose to focus on some new ways of addressing historical issues, which are based on databases which are now available at large scale, and especially bibliometric database, typically the Web of Science. And so what we would like to do in this study would be to see how the field, from its birth to its state now, has emerged as a new kind of a new paradigm and a new discipline, and how this can be read from data which come from publication, especially. And so what we choose chose to do was to look at this with a number of snapshots at different periods of times, and then to think about the dynamics of this and how this evolved and how this changed from the beginning to the end. So this is some work we are doing at TNS in Lyon, especially with Pablo Jensen, who is a physicist and was also interested in more economic problems, and Matteo Morini, which is an economist. So if we, I talk about the Web of Science. So if we ask the Web of Science about wavelets, you get a number of answers. So we can just enter wavelets at the keywords, and then you will get a fairly large amount of references. So this was a couple of years ago. I don't think it changed a lot. It was three years ago. Okay. The thing is that we have to do some pre-processing and some cleaning, because wavelets now has a meaning which was not necessarily the same meaning 20 years ago, 30 years ago, and 100 years ago. And for instance, if you look at the Web of Science, you see that you even have a reference here, which is 1926. So 1926 is certainly something which has not really to be taken into account. So if you are curious, because I think we have to be curious, then you can say, what is this paper about wavelets? That's gastric wavelets. Okay. And so that's typically a problem of that's a paper about gastric problems in which you have some form of oscillation in the stomach, and so there are some wavelets. And the thing which is funny is that history, in some sense, has a weird evolution, because if we just look a number of years later, in 2007, people using actual wavelets have been interested in analyzing exactly this type of data, which are the stomach wavelets. That was just for fun. But okay, so the methodology we used was I would say semi-informed. They're not totally blind. So we know something about the story, and so we do not go just in a blind way in all this stuff. But we think that there is one year which is especially important in this story, which is 1993. Why? For a number of reasons. First, this was 1 year where this wavelet literature survey has been published by people in Vienna, and this was a time where it was possible to edit in a booklet something which was a comprehensive and almost complete list of all the publications concerning wavelets, which now would be completely different. You would have something that big. And this is also the time where this started to begin to be a new keyword. For instance, in the IEEE Introduction of Signal Processing, which is one of the main journals for publishing results related to wavelets, wavelets were the object of a special issue in December. I was co-editor of the special issue in '93, and also it was by the end of '93 that wavelets appeared as a keyword in the edicts when you submit a paper. So this means something. And so what we were interested to do was to look at what is in this. And in this you have something which is about 20 books at that time, 1,000 papers and 700 authors. And so we can make some kind of distinction between what I would call the pre-wavelet actors of the wavelet story and wavelet natives. Because at the time where the field started, of course, it was thanks to people who were already either senior people, at least active people. Think about Alex Grossman, Yves Meyer, and Debussy. They were already active in this, but they were in other domains. But at the same time, there was a bunch of young people whose first research was devoted to this wavelet. The first PhD students working on wavelets with those more senior people. And this is what I call the wavelet natives. And also, and from this, we selected, at least we wanted to have people with at least 5 papers in this survey. And so we selected these were 82 authors and this number of articles. And of course, these people either had a life before and then the life continue, or we're starting with this and of course the life continue. And then we looked at what happened to all these people on the basis of some short time analysis over a period of times of 4 years, starting back earlier than this, of course, from 80, until a much more recent period of time, which is 2010. Okay, so we take these people and we look at either what they did before and how this evolved, or it just started and what happens next. Okay, and in order to have something which is a little bit meaningful, this is, of course, very empirical. We choose these 4-year snapshots, considering that with Fourier we can do some kind of statistical analysis, I would say, and then we overlap the different snapshots and we see some evolution. If we were at a shorter scale of time, 1 year or so, it would be much to variability, and at longer period of time we would get some smoothing. That's a non-stationary problem as usual, and so that's the short time window, which is ad hoc, I would say. Okay. So now, here is an example of what happens and how we can try to handle this from this network point of view. So when you look at some entry within this database, for instance, here you have a paper by Donovan and Johnston, which is a very famous paper, then what you get is an information which is related to the title of the paper, with a number of words in the title. You have journal, you have the authors, of course, and some keywords which are indicated, plus some references. And so with all of this, you can get some kind of a bag of information which are concerning this paper. And what we did was to consider the data as the records of the web of science from all these identified authors, I explained before, and then we try to structure this as some kind of interaction network where we will draw graphs in which the nodes are given by authors, references, keywords, disciplines, okay? And the links are related to the co-appearance in the same paper. And of course, you will have something which is bigger in terms of nodes in proportion to the number of times author, reference, keywords, disciplines, and so on and so forth are involved in the base. And in terms of the links, again, this is in proportion of the number of times you have the co-appearance in the same paper. And so this way we get some organization of this information in terms of what we can call communities in a common sense, like communities coming from maximizing, for instance, modularity in human sense, with a classical algorithm like the Louvain algorithm for achieving this maximum modularity. And what we choose to do, which is of course some reduction of the complexity of these heterogeneous networks, is to visualize this network by a system which is based on what is called a force-based algorithm, which somehow simulate, this is the GFE system, which simulates a physical system in which the node will be some charged particles which tends to be repelled from each other, and the links are corresponding to springs, and the springs tend, on the contrary, to attract these particles. And of course, the more heavy the force of the spring, the links, the force of the spring, and then you tend to aggregate this quality together. So if you do this, if you run the system, I do not enter into the detail, what you get is something which is this kind of landscape, okay? And in this landscape, you have a number of words, which can be either disciplines, mathematics, names, diamond, for instance, or keywords, estimation, or things like this, okay? And this is typically something which is referred to as before because it corresponds to the period 1980-1983. I remind you that what is widely accepted as a seminal paper of the field is a Grossman-Morley paper in 1984. So even if people were aware by preprints 1 year before, anyway, it's something which is before. And what we see here is that we have, think of this landscape as some islands on some ocean, okay, we have somehow some isolated islands. And you have big groups. For instance, the first one, which is really mathematics. And you see that in mathematics, the people who are interested which are ultimately interested in wavelets at that time were working on things related to approximation theory, essentially multivariate analysis, things like this, okay? You have another group, which is a big group in physics, mathematical physics, turbulence, a lot of turbulence with William Frisch, for instance, Arnaud Poulet, and people like this. And Ingrid Dobuchy was here more on the mathematical physics side. And we have a third group, which is in engineering, and people in automatic control, like Alan Welsky and Benveniste and other people. And you even have a small group here, which is somehow more heterogeneous, with things coming from general communication theory, with names like Gabor in terms of reference, and people doing early stages of time frequency analysis, also in optics, like Harold Zhu. Okay, this is before. And so now if you go, I told you that we take Fourier snapshots like this. If you go a bit later in time, you go to something which starts to get better organized. So now we see that as compared to the previous diagram, we still have the big islands, mathematics, physics, and electrical engineering especially, but you have this new, previously this was kind of one group, and then you have the mathematical physics, which starts a little bit to be more specific here, and here in this group you see explicitly this appearance of the grouping of Grossman, Morley, and Dobuchy. And when you look at the way, I agree, this is just a projection in 2D and so on and so forth, that's a visualization. But anyway, if you look at the big diagram, you see that this nevertheless starts to be some kind of link in between these different communities. And if you go a little bit further, and you go to the next period of time, 87 to 90, then you see more clearly that everything starts to be mixed up and to have a more homogeneous group, I would say. And in this case, you start to see in the middle of this wavelets appearing as one of the keywords, which is shared by all these different groups. And now many bridges have been constructed, not because there were walls before and bridges now, but there are bridges between the different islands. And when you go further to this next period, which was around this 93, that I call the maturity for looking at the emergence of the field, we see that now we have one kind of big group. And in this big group, of course, you have wavelets, Mala, Dobuchy, depending which paper is cited, for instance, and what can be understood a little bit more clearly, and I will just say something later, is that here the very seminal paper, the new seminal paper for this new life of wavelets is the paper by Ingrid Dobuchy about orthonormal basis, 88, which is one of the most important papers in this. Okay, so now we can have also some more maybe qualitative features, because here we look at things, and I think it's interesting because it goes with the interpretation we have a priori about this evolution. But as explained, it's a way of organizing the different references and names and so on and so forth in communities. These communities are referred to as islands. And so if you want to quantify this, you can see an evolution of the measure of this the importance of this community, for instance, in terms of modularity. And the modularity curve is here in blue. And when you look at this, of course, what you see is that you have a tremendous gap here, which is exactly around this period 90, 91, 92, 3, 4, here, okay, which correspond to the fact that whereas before you have mostly scattered groups with a modularity which was high, then everything tends to be collapsed in something much more structured, okay, the big group we saw before, okay, and then what is interesting is that afterwards you go back to something which evolved to a larger modularity. So just a matter of companion information, you have the number of authors, and you see that the number of authors start growing till this period and then tends more out to be stabilized, and the same for the degree of the in the graph. And so this may be explained in a number of different ways, and what I would like to claim, and which will be always supported by other arguments later, is that when you observe this kind of historical evolution, you have, in fact, at least, I would say, 3 steps. The first one, which is the before period, where things are more or less unrelated. Then you have some form of convergence, because everybody is starting to share common interest within a domain which is in construction. And this was exactly the time where we had big wavelet conferences where everybody from every field were together. But after that, of course, you get another evolution in which, on the one hand, I would not say that the construction of wavelets is over, but anyway, most of the things have been done from a theoretical point of view, and a lot of things now goes to applications and variation on this. And when you go to application, then you start being scattered again, because this was a period where you observed that you had conferences, wavelets in astrophysics, wavelets in biology, wavelets and so on and so forth. And so people who were, in some sense, born with wavelets, then took this tool and imported these tools in their own domain, and then used them in the domain, and not necessarily as something which is common, because after a while, for instance, now there is no real point, except from time to time for precisely historical reason, to have one big wavelet conference. We do not observe anymore that we have big wavelet conference. Wavelets is more something which is used in different contexts, or which is studied per se, but by mathematicians or by people from distinctive areas. So this is one way of thinking about how these paradigms are evolving or appearing, and I would say that we are in a typical situation where, for things to work, to be effective, in this kind of mix in between theoretical and applied science, we have to deal in a fairly balanced way in between with 3 components. One which is more rooted in physics, but physics at large, which means the world, natural science, maybe even the engineered world, okay? Mathematics, and also informatics. Why? Because you need to have something which is rooted in, which has something to say to the world and with the world, for which you can build some theory, and for which you might have tools which enable you to really implement and use this in an effective way. And this is something which is in between applied computational harmonic analysis, and this was exactly why this journal was created right after, which is applied computational harmonic analysis. And from the beginning, it was chosen not to call this journal Wavelets, for instance, because it entered this general philosophy from which wavelets is a very good example, but not the only one. Why? Because wavelets is one of the most prominent example of this trilogy here, because if you think of the way it appeared in the in science, it came from physics and geophysics, and the early works of Morley was in vibroseismics for oil exploration. And that was really the use of wavelets. Even the word wavelets was used in geophysics, not exactly in the same context, but this is something coming from physics. And almost immediately after, there has been a huge development in mathematics leading to many things. Of course, starting with the continuous wavelet transform with Alex Grossman, who was a theoretical physicist, but also the multi-resolution analysis developed by Malin and Meyer, all the bases developed by Gridovsky and other people, the frames and so on. So there is a complete renewal of, we could say, harmonic analysis, thanks to wavelets, and everything really developed and was accepted by the community at large, because at the same time there was a connection with computer science ideas related to filter banks and also to the existence of fast algorithms. So without the three of them, we would not have observed something that successful. And I would just like to say, to support this by making a comparison first with Fourier, which was the same kind of success. Because if you think of Fourier, Fourier basically was a physics problem, because it was to solve the heat equation. This was a problem formulated by the French Academy of Science, give a solution to the problem of heat equation, and Fourier handled this problem and developed for that a new branch of mathematics, which later turned out to be harmonic analysis. But the real success, this was well known in the 19th century, the early 20th century, but not that useful if you think of the way harmonic analysis was performed in the late 19th century and early 20th century. It was even with mechanical devices, things like this. For instance, there is this tidal machine by Lord Kelvin, which should be somewhere not far from here, and people were interested in optical solutions, and then, okay, computers, right? And with computers, in '65, there was this revolution of the fast Fourier transform. And the fast Fourier transform really made it possible to use this, and this notion of Fourier analysis, which was around, just spread in every area of science, and almost everybody is using Fourier analysis, be it in chemistry, in geophysics, in health, in bioengineering, in whatever. Okay, and this precisely has to be contrasted with other notions that I'm interested in in other domains. And for instance, if you think precisely of this idea of non-stationary signal processing that Sophia mentioned, and you have something which is extremely nice, which is called the Wigner representation of quantum mechanics, or for signal as well. And this is something also rooted in physics, because it aims at giving a semi-classical view of quantum mechanics. Forget about the operators, you do something as if you were in classical phase space, almost. Okay, and this is extremely nice. Nice idea, Wigner, 1932. And in mathematics, you have very, very, very nice ideas associated to that. And all the theory of pseudo-differential operators is related to that. But when you turn to applications, it's a little bit different, because you have no algorithmic efficiency. You have no fast algorithm. Everything is very complicated. Everything is nice in continuous time and so on. So it's a very, very nice framework from a theoretical point of view, but it's just lacking from being applicable easily. And now if you turn to something which is more recent, which by the way had been more or less proposed during this semester, Sophia was talking about in '98, there is a notion which is a little bit, which is related to that, which is called empirical mode decomposition, which is also aimed at decomposing complicated waveforms involving different non-stationary components in individual components, okay? And this is, as the name indicates, empirical, but it's nice because also it's physics at the base, and because it's a data-driven analysis, which makes sense just when you speak about the way it's constructed, looking at local extrema and so on and so forth. So it's rooted in physics in some way, and the good thing is that you can derive from this an algorithm which is extremely simple. and extremely effective in many cases. And so people are using that quite heavily in different fields. The problem is that there is no good mathematics associated to this, and no sound theory. So it remains empirical and more or less ad hoc. And okay, you should have 3, you have 2. And with 2 instead of 3, you cannot really succeed. So you cannot get the same success neither with this EMD thing, nor with a Wigner type distribution as you did with, for instance, Fourier and the Wavelets. So that was just a remark. And then what we did was to look at what happened in the beginning and until this 93, which is some kind of turning point in the evolution, and we can say what's next, what happened next. And if you look now at what happened, is that you see from the very beginning when you have nothing, this is a number of publications, number of papers. From nothing, you see an increase, and this increase is going on till, I would say, a little bit in between 2005 and 2010, and then we observe something which is some kind of, at best, a plateau. Okay. And here there are 2 curves, but okay, look at the black one. The black one is a raw number of papers, and the red one is something which has been weighted for taking into account the fact that globally the number of publications is increasing. I guess this is not big news that more and more papers are published every year. So you can also think about some form of relative proportion. And it's not that, well, there has been a renormalization, and then I will just renormalize to have the same number at the maximum. And so here is some kind of weighted compensation for this. And what is quite interesting is that in the first period, in some sense, when re-weighted, it seems that you have more papers than the actual, well, the growth of those specific papers is somehow higher than the growth of globally all the papers published. You can get in the Web of Science. And after it's a little bit the contrary. Okay, there is no error bars, and so on, but it's somehow a little bit the contrary in the sense that it could be some kind of lack of interest for the thing. And so we can try to think about this. Is this the end of the bubble? Why? And how can we interpret this? So I suggest a number of interpretations. Of course, the first one is that when the word wavelet is more and more accepted as a concept, it also becomes more and more accepted as a keyword, and it somehow disappears. For instance, if you write a paper and you use spectrum analysis, I don't think you will put Fourier in the keywords, okay? And it will be the same for wavelets. At the beginning, everybody was using wavelets, but after a while, okay, it's just a tool, and so it's trivial. So you do not use it as a keyword. And also, this is just make a remark, because I have no time to enter into all the exploration of the diagram. But when you look at what are the, I would say, the hub papers, for instance, which can be seen in those diagrams, you can look at those. And for instance, there's something funny. At the beginning, there was one paper extremely highly cited in chemistry. But I would say that almost nobody knows about this paper in the wavelet community. But this was just because when you look at the way papers were written at the very beginning, in each paper, the authors start writing, well, wavelets is an emerging field with already a number of applications in blah, 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 and citing different fields, and people were more or less obliged to cite one paper in chemistry, and there was one that was always the same, important or not, and this paper got much more credit than other papers, but not necessarily for the best reason, because after it was not cited anymore, and so just to to say that there could be some bias in the analysis and you have to carefully look about the data. But, okay, anyway, I think this interpretation of wavelet becoming a keyword is relevant. The second one is that there is some kind of renewal. Because people doing wavelets at the beginning maybe do something else later on. And in the introduction, I just remind you that one of the main important properties of wavelets is that they sparsify data. And sparsity become really a keyword in the, I would say, mid 2005 or something like this. And with this arrived this notion of compressed sensing. I don't know if you know about compressed sensing, but this is something which was pushed forward by David Donoho, especially, and Emmanuel Candes, and some other people, and which really is intended to favor sparsity. So, in a nutshell, rather than taking data, going to the wavelet domain, and say that in the wavelet domain only 10% of the samples are useful, just kick out 90% of the data and come back, the approach more or less amounts to directly select the 10% that are useful. So you compress at the level of the sensing and not afterwards as a post-processing. And this was an incredibly active field in between 2005 and 2010, and mostly by people who were previously involved in wavelets. First, because they were aware that the wavelets were sparsifying tools and were good for approaching compressed sensing problems, and because this was related. So if you look now at this combined evolution, you see again the black curve as before, and here is the curve of the compressed sensing related papers. You see nothing before 2005, and then also an increase. And if you look at the combined evolution of both, you see that for about the same community, that you still get some increase. So if you can consider that, given the people were interested in the kind of studies related to wavelets at large, some of them just switched to compressed sensing idea, but that was more a different way of balancing who was doing what. And globally, you get still some kind of evolution. And the other point is that now you have new form of landscapes. And for instance, this is an example of the exactly with the same tool, without too much pre-processing. If you are not really careful, what you get is something like this from 2007, 2010. And when you look at this, you see now something which is a little bit different as compared to before, because first we get really the score of wavelet analysis, which could be interpreted as the follow-up of what was observed before, with everything mixed together, computer science, engineering, applied math, and so on, and some stats and things like this. But you also see something which is a little bit different, because here you get a very, very large component which is related to especially astronomy and astrophysics. And this has a weight for two reasons. The first one is that a lot of people invested on this in specific application domain, and especially in astronomy and astrophysics. And as you may know, in astronomy and astrophysics, very often the list of authors is longer than the paper. So it's something which is big science, and so this creates a bias which is mostly due to the fact that when you have a math paper about wavelets with 1, 2, or 3 authors, you might have something with 500 authors. And when you put this without some care, you get something. But which has an interpretation, so it's not nonsense, it's just that you have to. Okay, so final point, just elements about the evolution I was talking about in the beginning. What I showed you were really snapshots. So I took snapshots for you, and visually we can accept the idea that they are changing a little bit the landscape, but can we do more, and can we go from snapshots to a form of genealogy for the field? And for this, we made preliminary experiments where you use some alluvial Sankey diagrams where you have flows for describing the evolution of communities. And in this case, what we do is that we consider the communities themselves as nodes. And for instance, this will be done with respect to a co-publication graph. So we consider communities which are formed by the fact that the papers are sharing, have common references. And then from one snapshot to the other one, we use a Jacquard index, which is essentially the size for two sets, the size of the intersection compared to the size of the union as the weight for the edge. So the more they are similar, the heavier the weight. And this way you can see how you can make growing some given community or just make disappear some community. Okay, then there are algorithmic issues for selecting the nodes and organizing them. I will not comment this. I just show you something which is not easy to see because there's a lot of information and it's much better when you go to a screen and you have a clickable version. But okay, so especially because here you have something which is completely global from the 70s to now, I would say. But the idea is to have this kind of flow diagrams where you have at each time, each year, considering again that 1 year is in fact something which is related to 4 years around this one, and you have an overlap from 1 year to the other one. Okay, you have different communities which are, in this case, indexed by the most frequently cited author in the community. There could be other ways. And then you see how you have communities which can come bigger and bigger and eventually disappear, and how you have these weights, these flows, which reorganize the different communities. So globally, what you observe is that the number of communities is increased. We go from left to right. At some time, you have some strong organization, and other times you have other ones, and I don't know why there should be some color box on the top of them. Okay, but here, when you just look at two specific period of times and you zoom in on this period of time, you can get a little bit more readable version. And this is, for instance, a genealogy for a period of 1990 plus or minus 5 years. Okay, and which really correspond to, I would say, the importance first of what is related to the Doboshi paper, and this is 1988 precisely, and then the way this paper diffused in different fields, and where especially here you have the ramification with Betterly, and then here you have things which are related to Chewy. So for people who know, this is approximation theory, and this is Groeschning, and this is pure math. And here, Betterly, this is electrical engineering. And after that, some people like Michael Woozer, who is extremely prolific in publication, did some kind of merging of all these ideas in image processing, and then you have a follow-up of others. So you can read something about this evolution, and so when you trace back, you can see what are the ancestors of a given important contribution, and go back to see that everything comes more or less from this key author or key paper. And if you look now at the second period, zoom number 2, here in this diagram, this is the emergence of the compressed sensing. And this is attached in this case to the name of Rich Barniak, because he's also one of the most prolific authors in this in this period of time, and this is something which really is observed and can be obtained from the reading of this diagram. So you can think about learning more about that diagram, but that's two examples which really illustrates some key points which are more or less already known, of course. So the conclusion and the question is, so good, so far so good, but did we learn something? And so it's difficult to answer this question because of course, this is not a complete study, yes. But this is also something which is not completely blind, as I told you. There's some part of informed analysis, and the interesting thing is that you can mix and cross perspectives, and also you can think about the role of experts. For example, experts were useful for selecting the initial group of authors, okay? But now you can also have some feedback. The good thing is that Wavelet theory is young and most of the actors are wrong. And they can give some feedback about that. It is the way you, when you do this semi-automatic analysis, and we extract from this kind of results interpretation, is this corresponding to your feeling about the evolution of the field? Do you recognize, okay, apart from looking for your name in the diagram, do you agree with the global evolution? And so this can be a feedback which could be useful. This is this is some form of contemporary history which might be useful. And the next thing, of course, is that here wavelets were used as a case study for an approach. And the idea that if this proves reasonably effective for describing what happened, maybe we didn't know much, we did not know something new about the evolution, because we knew about the field, especially as insiders and so on. But this can help us trusting a little bit more the results if now we would apply this very same tools to another field. For instance, if I do not know anything about microbiology, for instance, but I guess that there are problems more or less similar with new concepts and so which happen. So if I apply in a semi-blind way the same tools to a domain I do not know, I will get something. So what can I say about this? Okay, maybe if we have these results which are reasonable for what we know, we can trust a little bit more for new discoveries in other domains. And of course, we can open a debate about okay, how to use and misuse bibliometric data, because here we chose to do that on this Web of Science. Okay, this is part of the information. This is not all of the information, but that's exactly as for the evaluation of researchers. Thank you.
So you developed tools where you can really zoom in on features and recognize communities and important actors. How hard would it be to build a mathematical model of the process where those two tools could have reliable properties?
I don't know. No, this is well, we are in discussion, for instance, with people, which is okay. There are different ways of building the communities, and especially in the recent past, there has been an interesting way of building communities, which is to use wavelets on graphs. And so, if you consider this as graphs, then, okay, you can try to approach this by tools which are able to structure the information in a graph in communities. And among these, one of the new ones which are more amenable to a theoretical analysis, maybe like classical tools, like classical algorithm like Lyon, Newman modularity, and so on, could be based precisely on wavelets. So, which is some kind of funny because it's, it will be wavelets, but this is in the infancy. I have no idea of whether this is really applicable to that. But the point is that in this case, you could have more mathematical control on what you are doing.
And then there's the other thing that, in a sense, the scientists were taught that the citation numbers per se don't matter. It's who was first and who did what. Like Strömberg is not in your
well, yeah. Maybe. Well, we have to. Of course.
Oh,
but,
it's inevitable.
Yes.
It's impossible not to miss things.
But it's difficult to. Well, Strömberg should be somewhere. But you know, even Morley is not easy to find. Because Morley didn't, well, it depends, but after a while, people were not citing Morley anymore. And it didn't publish a lot. It published at the very beginning, and after that, well, also Morley was okay, in a difficult position, and he was not publishing, well, he was in a private company, he was not really private, in industry, I would say, and he was not publishing a lot, and also he was very reluctant to publish. I don't know if you knew Morley.
No.
So he was kind of reluctant to publish, and then he published with Grossman, but a couple of papers, very few.
But that sort of brings back the model, because what are you actually trying to study with the analysis? Is it the observed number of citations?
Yes, yes.
Which is an observable quantity, or is it the importance of something to the development of science, which is
Yes.
an ephemeral silliness,
Yeah,
right?
no, that's a little bit this line, because you cannot just trust only on numbers, and that's exactly the remark I made at the end. Exactly as for evaluation of individuals now, okay, you know that you have more important people who have less papers with higher impact, which is not necessarily a direct impact in terms of. Okay, so I don't claim this is the only way, and this is a line, not only one perspective. This is one way of approaching the thing. The other one, which is the fame that people can get. There are some. Well, everybody. Yes, everybody knows. I take this example of Morley because everybody, Wavelets, know that Morley is important, and nobody is citing Morley anymore, almost. Whereas there has been now some textbooks by important people as well. You think of the book by Ingrid or by Stéphane Mallard, and those now can be cited because very often well, now also something which is more difficult if we want to go on with this approach, that you have complete changes in the publication process. At that time, we were still in a phase where you had either books, papers, and a few preprints. Okay, but now we are at a stage where most things are first on archive and eventually published in journals, but maybe people are not, are already considering what is important from the preprint and not waiting for the paper to be published, and books are a little bit different elsewhere. So it's more, and for instance, even in the seminal paper by Gay-Doveshi on autonomal basis, it has been 2 years in between the preprint which circulated in the community. Everybody had the preprint at Bell Labs and ATT, and eventually it was published at Communication in Pure and Applied Mathematics in '88. But when it was published, everybody was already using the algorithms and previously was citing. And the same problem occurred more recently because we had hard time to trace back the emergence of compressed sensing, for instance, with this Baraniuk flow. Because if you think of the 2006-7, which was right after the paper by Dono in information theory and the paper to appear by Candes and Romberg and Tao, then most of the things were only preprints. And you had some papers in which all the reference lists are only preprints. So it's more difficult to handle, I think, because okay, it's not clear, and it's not clear that after that, even if the paper is published, people will everything is going at a different pace now.
Sorry,
No.
other people have questions.
I have a short question. Say, is it possible to develop some kind of prediction based on network information, same way as you can do, I don't know, node prediction or link prediction, where wavelets will develop into the future?
I won't say that. No.
Or at least which I don't know, which other application domain they're going to penetrate or something. Not
Yes.
how it will develop per se methodologically, but at least, you know, by looking what fields wavelets we used before.
I'm not sure.
But
Wow.
potentially other,
Wow.
I mean, like doing almost like overlapping communities. and
Yes,
seeing like
yes.
what could be.
No, you can make. Well, maybe you can make very short-term prediction just because of the fact that when you see the number of people who are investing in the field for well, you can expect that for a while they will go on, but I'm not sure that we can do some. Well, you can also. That's the problem of projecting what happened in the past to what could happen. For instance, people are using the H index to predict the future of individuals. So I'm not sure it's exactly what has to be done, but Hirsch first was to propose that looking at records of what people did at some period when in the early development of the career and what was their evolution, and in the evolution of these indexes, when you look at the actual current status of indexes for people, he claimed that he could infer something about the future. I won't.
But also we see in your diagram there were individuals like Stack and Marta who did things in Astro. Those people had not existed. I doubt that whole particular sub-branch would have existed, and that's why I think it's impossible.
Well, I guess short-term, I don't think it's possible to get, I don't even want to say individual prediction, but I mean kind of a trend where it's gonna go. Like, like almost like how statistical genetics has developed, yes? So you can track what was the critical mass of knowledge every time. And
if you wanted to predict that, wouldn't you go in terms of research council investment in genetics? Right.
Well, if you do it slightly earlier than that, obviously. So like I'm asking, just say, I mean, in US now there's been discussion where what will be the main areas after Trump, what the key areas, yes? So it's just a general question because you have all this great data on wavelets. So by looking for network components and how different areas interacted, like almost like you started from 1920 paper and then.
Well, okay, I understand. Yeah, I think that I understand a little bit more what you said. I think that something which is a little bit different from this specific study about wavelets is that you can learn something at the level of institutions, at the level of communities in country, international levels, how people are a little bit reorganizing in kind of new fields because of for instance, the question is what makes here we are interested in identifying communities and looking at the evolution. So what makes a community, not from a mathematical point of view, but what makes that, for instance, you consider that you are part of a given community? Could be statistics, could be mathematics, could be genetics, I don't know. It's mostly because you share a number of things with other people. You have common references. In the paper you have, you can talk to each other because, of course, when you say something, this is understood by the other people because you share all these common references. And when new fields are reorganizing, then you can identify those new fields precisely by looking at what are the common
mass.
Yes, exactly. And for instance, a number of years ago, for instance, the field of neuroscience was not existing per se, but now it's very difficult to classify neuroscience. It's part of, it's in overlap with many other well-identified classical fields, but anyway, it's something which has its own right. And at a more modest level, I'm a signal processing guy, and signal processing was not existing as such 30 years ago, but now it's considered as something. But of course, it used tools from statistics, from harmonic analysis, from from physics for computer algorithms and so on. But anyway, there is something which makes that people doing signal processing recognize themselves as belonging to the same community and attend the same conferences and so on. And so you can think of measuring this. Well, this would be, well, classically, if you look at the 19th century, we had this classification of science coming from in France from Auguste Comte, and you have a number of domains in maths and so on. And then you try to be in this in one slot which corresponds to what you are supposed to do, and this is still a little bit the case for the organization of science when you apply for grants. But this is, I would say, a top-down approach. So you first create the categories, and then you try to manage for being in one of the categories. And now this helps having more a bottom-up, data-driven approach, where you start from what exists, and you see how from what exists you can find some ordered organization which maybe will be a little bit different. Clearly, people doing algebraic geometry will go to algebraic geometry, but people doing things which are more related to vision, for instance, it's not clear where they will be exactly. I'm not speaking about data science, for instance, now.